Shift registers. Registers are used to store group of bits. In registers to store n bit equals n flip-flop. The serial input determines what goes into the leftmost flip-flop during the shift. Depending upon input and output, registers can be classified into four types: SISO, serial in, serial out; SIPO, serial in, parallel out; parallel in, serial out; parallel in, parallel out. In SISO, 4-bit right shift SISO register. In right shift SISO register, LSB data is applied at the MSB flip-flop, that is brackets D flip-flop. If n-bit register to enter n-bit data, it requires n clock pulses in serial form. If n-bit data is stored in SISO register, then output is taken serially. For this, n-1 clock pulses are required. SISO register is used to provide n clock pulse delay to the input data. If t is the time period of clock pulse, then delay provided by SISO is nt. 4-bit left shift SISO register. In this above SISO register, MSB data is applied to the LSB flip-flop, D flip-flop. To enter the n-bit data in serial form, we require n clock pulse. To exit or getting output of n-bit data as serially, we require n-1 clock pulses. SIPO, serial in, parallel out. For n-bit serial in, parallel out, n-bit serial input data to be stored, the number of clock pulse required equal to n. For n-bit parallel output data to be stored, the number of clock pulse required equal to 0. There is no need of clock pulse. Parallel in, serial out. To store parallel in data, if we store n-bit, then the number of clock pulse required equal to 1 clock pulse. To store serial out data, if we store n-bit, then the number of clock pulse required equal to n minus 1. Note: to convert temporal code into spatial code, we use SIPO register, whereas to convert spatial code into temporal code, we use PISO register. PIPO for parallel in data, the number of clock pulse required equal to 1 clock pulse. For parallel out data, the number of clock pulse required equal to 0 clock pulse. Remember, all shift registers are made of JK flip-flops. PIPO register is a storage register made up with D flip-flops. Clock pulses required by various shift registers. SISO input n-th output n-1. SIPO input n-th output 0. PISO input 1-th output n-1. Whereas PIPO, the input clock pulse 1-th output clock pulse required is 0. If n shift left operations are performed, then data will be multiplied 2 power n times. If n shift right operations are performed, data will be divided by 2 power n times. Time delay SISO SRs may be used to introduce time delay delta t in digital signals. Delta t equal to n into capital T, n into 1 by fc. N is number of flip-flops, T is time period, and clock pulse. Fc equal to clock frequency. The amount of delay can be controlled by the Fc or number of flip-flops in the SR. Counters. It is a sequential circuit formed by the cascading of flip-flops. Counters are basically used for counting of the number of clock pulses applied. Frequency division, frequency measurement, timers, waveform generations. Counters are classified as asynchronous counter, synchronous counter. Remember, if n equal total number of states and small n equal number of flip-flops, then capital N is less than or equal to 2 power n. Small n less than or greater than or equal to 3.32 log 10 base n, log n base 10, or small n greater than or equal to log capital N base 2. If n equal to 2 power n, then we get a binary counter. If capital N is less than 2 power n, then we get non-binary counter. The mod number indicates the number of states in counting sequence. For n flip-flops, counter will have 2 power n different states, and then the counter is set to be mod 2 power n counter. Mod number indicates the frequency division factor obtained from the last flip-flop. It would be capable of counting up to 2 power n minus 1 before return to 0 state. Note: in modern counter, if applied input frequency f, then output frequency is f by n. If two counters are cascaded with mod m followed by mod n, then the number of overall states combined counter is m into n, and counter is called mod m n counter. Asynchronous or series counter, binary ripple counter, JK flip-flop, MSB, LSB clock pulse. In ripple counter with n flip-flops, there There are 2 power n possible states. With n flip-flops, the maximum count that can be obtained counted by this counter is 2 power n minus 1. If input frequency f, then the output frequency is f by 2 power n. It is also known as 2 power n is to 1 scalar divider for proper operation of the ripple counter. T clock greater than or equal to n TPD flip-flop. F clock is less than or equal to 1 by n TPD flip-flop. Maximum clock frequency equal to f clock comma m equal to 1 by n TPD flip-flop. Disadvantages of ripple counter. Decoding error is present due to propagation delay of flip-flops, that is TPD flip-flop. Up or down counter. An up or down counter can count any direction depending upon the control input. For determination of up or down counter, triggering with negative edge, clock connection Q acts as upper counter. Triggering with negative edge, clock connection is Q bar acts as down counter. Triggering with positive edge, clock connection is Q acts as down counter. Triggering edge, positive edge, clock connection is Q bar acts as up counter. Non-binary ripple counter, decade counter or mod 10 counter. In non-binary ripple counter or decade counter or mod 10 counter, use states equal 10 and unused states equal 6. Output frequency of mod 10 counter equal to f by 10. Clear and preset is used in binary non-binary ripple counter. Clear is used to reset counter without clock. Reset is used to set counter. When decade counter counts from 0 to 9, then it is known as BCD counter. Synchronous or parallel counters. Ring counters. It is a SISO shift registers. Ring counter is a non-self starting counter. With n flip-flops, there are n states present in a ring counter. With n flip-flops, maximum count possible in the ring counter is 2 power n minus 1. Decoding is very easy in ring counter because there is no aid of the extra circuit. Ring counter is a non-self starting counter. Okay, now in a 4-bit ring counter, used states equal 4, unused states equal 2 power 4 minus 4 equal to 12. In a ring counter, if clock frequency is f, the flip-flop output frequency is f by n, where n equal to number of states equal to modulus of the counter. Twisted ring counter, also known as Johnson counter or switch rail ring counter. With n flip-flops, there are 2n states in the counter. With n flip-flops, the maximum count by this counter is 2 power n minus 1. If in a normal Johnson counter with n flip-flops and input frequency is f, then the output frequency of flip-flop is f by 2n. Synchronous series carry counter. Clock frequency of clock is less than or equal to 1 whole by మొత్తానికి TPD flip-flop plus n minus 2 into TPD of AND gate. F clock is less than or equal to 1 whole by TPD flip-flop plus n minus 2 TPD AND gate. Synchronous parallel carry counter. It is the fastest counter. Clock frequency f clock equal to 1 by TPD flip-flop plus TPD AND gate. Digital ICs family. A group of compatible ICs with the same logic levels and supply voltages to perform various logic functions fabricated using a specified circuit configuration is called logic family. Characteristics of logic family. Propagation time delay. This is the average transition delay time for the signal to propagate from input to output. When the signal changes its value, that determines how fast the logic system can operate. Delay time equal to TPD equal to TPHL plus TPLH by 2 nanoseconds. TPLH means delay time in going from low state to high logic state. TPHL, delay time in going from high logic state to low logic state. The delay times are measured between the 50% points on the input and output transitions. In BJT, TPLH greater than TPHL due to reverse recovery time. In fact, TPLH less than TPHL due to large capacitance informed. Power dissipation PD is the amount of power dissipated in IC determined by the current ICC, which draws from the VCC supply. Collector current ICC equal to ICCH plus ICCL by 2, where ICCH current value when all inputs are high, ICCL current value when all inputs are low. Power dissipation PD average equal to ICC into VCC milliwatts. Figure of merit. FOM equal to TPD into PD average picojoules. The best operation of IC is figure of merit to be as small as possible. TPD into PD average. Fan in and fan out. The maximum number of inputs which can be applied to a logic gate is known as fan in. On the other hand, fan out of logic is the number of wires that can be driven by it. Fan out equal to IOH by IAH or IOL by IAL, whichever is minimum. Fan out equal to IOH by IH or IOL by IL, whichever is minimum. Noise margin is the property of a logical circuit To withstand unwanted noise voltage at input or the maximum voice value of the noise signal that a system can reject with performance unaffected. VOH greater than VIH greater than VIL greater than VOL. High state NM noise margin equal to VNH equal to VOH min minus VIH min. Low state noise margin VNL equal to VIL max minus VOL max. Noise margins equal to minimum of VNH comma VNL. RTL provides wide and logic. Direct coupled transistor logic provides wide and logic. It suffers from current hogging. HOGGING. Direct coupled transistor logic means Y equal to A plus B plus C whole bar. Resistor transistor logic Y equal to A plus B plus C whole bar. Diode transistor logic DTL provides wide and logic Y equal to ABC whole complement. High threshold logic HTL. High threshold logic consists has circuit has excellent noise margin and largest voltage swing. It provides wide and logic. TTL transistor logic. TTL circuits are classified as tri-state logic, high impedance logic, totem pole logic, active pull-up, totem pole logic, active pull-up, tri-state logic, high impedance logic, open collector logic, passive pull-up, tri-state logic is used in bus-oriented systems. Totem pole logic does not provide wide logic. The disadvantage of active pull-up or passive pull-up is reduced power dissipation, increased speed operation. The advantage of active pull-up or passive pull-up is reduced power dissipation and increased speed operation. Any floating input TTL is considered as logic 1. Floating input of TTL is considered as logic 1. Emitter coupled logic. Emitter coupled logic ECL is a non-saturated logic. It is the fastest logic among all and hence called current mode logic. It provides wide OR logic. It uses negative power supply to avoid noise and glitches. Any floating input in ECL is considered as logic 0. Integrated injection logic I2L logic has a best figure of merit. MOS logic family. MOS digital ICs use enhancement MOSFETs exclusively because of the symmetrical construction of source and drain. The MOS transistor can be operated as a bilateral device. N-channel MOS, it is faster than PMOS. NMOS conducts whenever input is high. P-channel MOS, also called pull-up network. PMOS uses FETs having heavily doped P-channel. PMOS conducts whenever input is low. Complementary MOS. CMOS is a combination of NMOS and PMOS and is fabricated as twin tub. Various logic functions can be realized using CMOS. They are characterized by low power dissipation and excellent noise immunity. Y equal to A dot B whole bar. Y equal to A plus B whole bar. Power dissipation in CMOS is of two types. Static, it will be present during logic 1 or logic 0. Dynamic, it will be present during logic level transition. PD dynamic equal to CF VDD square. C is capacitance, F equal to frequency, VDD means supply voltage. Comparison of various logic families, very important. Logic parameter RTL, basic gate, NOR, fan out 5, power dissipation in milliwatt is 12, TPD nanoseconds is 50, figure of merit is 500, noise margin equal to 0.2 volts. Now if we come to DTL, basic gate is NAND, fan out is 8, power dissipation in milliwatts is 8 to 12, TPD is 30 nanoseconds, figure of merit is 240 picojoules and noise margin equal to 0.75 volts. HTL, basic gate is NAND, fan out is 10, power dissipation is 55, TPD nanoseconds is 90, figure of merit equal to 5000, whereas noise margin of voltage equal to noise margin of voltage equal to 4 to 5. TTL, basic gate is NAND gate, fan out is 10, power dissipation is 12 to 22 milliwatt, propagation delay TPD nanosecond is 12 to 6 seconds, figure of merit equal to 144 to 132, noise margin equal to 0.4 volt. ECL, R and R లేదా NOR, fan out is 25, power dissipation is 40 to 55, super milliwatt, power is more dissipated, not super. TPD nanoseconds is 4 to 1 nanosecond, the figure of merit is 55 to 160 in picojoules and noise margin is 0.3. MOS, NAND or NOR, fan out equal to 20, power dissipation is 0.2 to 10, TPD in nanoseconds is 300, figure of merit in picojoules is 60, Noise margin voltage equal to 1.5. CMOS basic gate, NAND and NOR gates, fan out is greater than 50, abnormal fan out. Power dissipation is very less, 0 to 0.01 TPD nanoseconds. Propagation delay is moderate, 70, whereas figure of merit is 0.7 picojoules. Noise margin equal to VDD by 2. DACs and ADCs, digital to analog converters. Specification of DAC. Resolution of DAC is change in analog voltage correspond to LSB bit increment at the input. Resolution equal to VR by 2 power n minus 1, where VR is nothing but reference voltage corresponding to logic 1. N equal to number of bits. Analog output voltage. Resolution into decimal equivalent of binary data equal to output voltage. Analog output voltage of an n bit straight binary DAC V naught equal to K into 2 full k into full 2 power n minus 1 b n minus 1 plus 2 power n minus 2 b n minus 2 plus and so on 2 power 2 b2 plus 2 power 1 b1 plus b naught, where k is the proportional constant, bn is nothing but 1 if the nth bit of the digital input is 1, 0 if the nth bit of digital input is 0. Full scale output voltage VFS maximum voltage is maximum output of DAC equal to VFS equal to resolution into maximum decimal VR by 2 power n minus 1 into 2 power n minus 1 equal to VR. Percentage resolution equal to resolution by VFS into 100, that equal to 1 by 2 power n minus 1 into 100. Error or accuracy. Maximum error acceptance in ADC or DAC is 1 LSB bit, which is equal to resolution. Weighted resistor DAC output voltage V naught equal to minus IF into RF. Output voltage V naught equal to minus IF by R into B naught by 2 power n minus 1 plus B1 by 2 power n minus 2 and so on, Bn by 2 power n minus 1 into VR. Resistance equal to LSB resistance equal to 2 power n minus 1, 2 power bracket of n minus 1 close bracket into MSB resistance. The resistance values are weighted in accordance with the binary weight. Here op amp is employed as a summing amplifier. Op amp is used in negative feedback mode to work as a current to voltage converter for n-bit DAC. Number of different levels equal to 2 power n. Number of steps equal to 2 power n minus 1. R2 to R ladder DAC by using non-inverting op amp. Gain of op amp V0 by V reference equal to 1 plus RF by R1, where RF is the feedback resistance, R1 is the input resistance. Output voltage V0 equal to V reference by 2F into sigma I equal 0 to n minus 1, 2 power I Vi into 1 plus RF by R1. R2 to R ladder DS by using inverting op amp. Same output voltage V0 equal to V reference by 2 power n into I sigma equal 0 to n minus 1, 2 power I Bi into minus RF by 3R. Output current I equal to V reference by 2 power n into sigma equal to 0 to n minus 1, 2 power I Bi into 1 by 3R. Resolution of R2 to R ladder network is VR by 2 power n. Inverted ladder R2 to R type DAC. For n-bit DAC, V0 equal to V reference by 2 power n into sigma equal to 0 to n minus 1, 2 power I Bi into minus RF by R. So R1 current IF equal to V reference by 2 power n into sigma equal to 0 to n minus 1, 2 power I Bi into 1 by R. On off switches S0, S1, S2, S3 are the same potential. You always consider that the bit as MSB, where the input reference voltage are supplied to be given. The bit stream B3, B2, B1, B0 base 2 has MSB equal to B3 and LSB equal to B0. Analog to digital converter. Specification of ADC. Voltage range Vmax minus V1, resolution equal to V range by 2 power n minus 1, that equal to 1 by 2 power n minus 1 into 100. Dynamic range equal to 1.8 plus 6 n dB. Types of ADCs are counter type, dual slope type, successive approximation resistor type, flash type. Counter type ADC. Number of clock pulses required for n-bit conversion equal to 2 power n minus 1. Maximum conversion time equal to 2 power n minus 1 into T clock. Counter type ADC, also known as ramp type ADC. In this ADC, conversion time depends on input voltage, input analog voltage. Flash type ADC. For n-bit conversion, flash type ADC requires 2 per n minus 1 comparators, 2 per n resistors, 1 2 per n by n priority encoder. It is the fastest ADC among all. It is also known as parallel comparator type ADC. SAR type successive approximation, residual type ADC, number of clock pulses required for n bit conversion equal to n, maximum conversion time equal to n into t clock. In SAR, ADC conversion time is independent of input voltage. In SAR, ADC conversion time is independent of input analog voltage. Dual slope integrating type ADC. Total number of clock pulses required equal to 2 per n plus capital N, that equal to 2 power full n plus 1. It is most accurate ADC, therefore mostly used in digital multimeter. It is slowest ADC. Dual slope integrating a type ADC is used in multimeter. It is a digital voltmeter. In digital voltmeter, it is used in slowest ADC. Remember, digital voltmeter means dual slope integrating type ADC. Next, remember counter type number of clocks 2 per n minus 1 time 2 per n minus 1 t clock. SAR number of clocks n time n t clock. Counter type number of clocks 1 time t clock. Counter type number of clocks 2 whole power n plus 1 time 2 whole power n plus 1 t clock, where t clock is clock time period. Okay, now ROM, the read-only memory is also called as mask ROM. The information is inscribed in the form of presence of or absence of a link. PROM, the programmable read-only memory. PROM are ROMs which are field programmable but lack erase capability. EPROM, EPROM stands for erasable programmable read-only memory. The presence or absence of a charge in the floating gate of a double polygate MOSFET determines the logic state. EEPROM, EEPROM stands for electrically erasable PROM. Programming and erasing in EEPROM is achieved by forcing the channel current to flow between the gate and substrate. SRAM, static random access memory, can retain stored data indefinitely. It can be implemented as a flip-flop circuit to store one bit of information. DRAM, dynamic RAM, uses a single transistor to access the capacitor's charge. Since the stored charge is gradually lost because of space charge generation or decomposition process, cells have to the read and refresh intermittently. Difference between RAM and ROM: RAM, it is a read or write memory. ROM, it is a read-only memory. Random access, time required to access any memory is same. Random access, volatile memory, temporary data storage, permanent data storage. Static RAM, dynamic RAM, very important. Both are RAMs, but static and dynamic is different. Static RAM, data is stored like flip-flop. Dynamic RAM, data is stored in MOS capacitor. Static RAM, BJT MOSFET is used. Dynamic RAM, MOSFET is used. Static RAM, faster. Dynamic RAM, slower. Static RAM, power dissipation is more. Dynamic RAM, power dissipation is low. Static RAM, density is less. Dynamic RAM, density is high. Static RAM, used as cache memory. Dynamic RAM, used as main memory. Static RAM, no refreshing is required. Dynamic RAM, refreshing is required. Finite state model or machine. The finite state machine is an abstract model that describes the synchronous sequential machine. In a sequential circuit, the output depends upon the present input as well as the past history, and therefore it would need an infinite capacity for storing them. Since it is impossible to implement machines with infinite storage capacity, finite state machines are used. Thus, finite state machines are sequential circuits whose past history can affect their future behavior in only a finite number of ways. That means finite state machines are machines with a fixed number of states. Every finite state machine has a finite number of memory devices. The block diagram of finite state machine is the shown figure. Here x1, x2 and are the inputs, y1, y2 are the outputs, z1, z2 are the state variables, and z1, z2 and capital Z1, capital Z2 are the represent the next state. With an n state machine, we can generate a periodic sequence of less than or equal to n states. Finite machines are of two types. The major difference between them is the way the output is generated. They are Moore type, Mealy type mode. Finite machines lone Moore type, finite machines lone Mealy type mode. Mealy machine, the output depends on current input and state. That means the output is derived from the combination logic, whereas less number of states are involved. This is very complex. Moore machine, the output is directly taken from memory state instead of combination logic. Output depends only on current state. More number of states are involved. It is relatively less complex to implement. The difference between Moore machine and Mealy machine, which are both are of finite state machines. Moore machine, the output is a function of present time state only. Mealy machine, the output is a function of present state as well as present input. The change in input does not affect the output of the circuit. The change in input may affect the output of the circuit. మీలేలో మూర్లో మూర్లో మెమరీలో తీసుకుంటాం కదా. ఫర్ ఇంప్లిమెంటింగ్ సేమ్ ఫంక్షన్ ఇట్ రిక్వైర్స్ మోర్ నెంబర్ ఆఫ్ స్టేట్స్. ఫర్ మీలే మెషిన్ ఇట్ రిక్వైర్స్ లెస్ నెంబర్ ఆఫ్ స్టేట్స్ ఫర్ ఇంప్లిమెంటింగ్ ద సేమ్ ఫంక్షన్. మూర్ మెషిన్లో ద డిజైనింగ్ ఆఫ్ మూర్ మోడల్ is easy, whereas మీలే మెషిన్లో ద డిజైనింగ్ ఆఫ్ మీలే మోడల్ is complex. State diagram. A state diagram represents a state machine, contains circles. They represent machine states labeled with a binary encoded number. Directed arcs, they present transition between state labeled with input or output for the state transition. SKSJ, state table. A state table expresses system behavior and consists of present state. It is a typical given by binary encoded form with SK inputs, the external input used to cause state transitions. Next state, the state which occurs after transition expressed in binary encoded form of SJ. Output which occurs other than the state. Note that there would be no outputs in Moore machine. Moore machine lo there is no outputs. Applications in sequence detection, vending machine designing, electronic design, automation, commutation protocol design. A sequence detector is a sequential machine which produces an output 1 every time when the desired sequence is deleted and an output 0 at all the other time.